All right, so here's the next question we're going to answer. Okay, here's a proton, and there's a proton. What does this proton or positively charged particle do to this guy? Repels him. Okay. So here's this proton, here's that proton, and repels him. How does it repel him? They're not in contact. Here's this proton, there's this guy in New York. He repels him. How does he repel him? They're
This would be like magnetic force,
so
rotational.
so to answer that question, here's the story we came up with. This proton creates a field all around it, all the way to infinity. This guy is just feeling the local field. He doesn't know what created it. Okay? And he doesn't care. So this guy is creating a field all around him, and there could be a bunch of people creating a field. This guy is just reacting to the electric field where he is located. Okay? So that's field forces. And that's what this thing is showing. This is just pictures. Here's a positive charge and here's a negative charge. This, by the way, is called a dipole. If you have equal and opposite charges, they're a dipole. They have to be equal and opposite. Okay? And what this is showing is these are field lines. What these field lines show is if you're at this location, the field at this location is tangent to there, okay, to that line. And you will learn in a second that if you put a positive charge, that's the direction in which it'll move. If you put a negative charge, it moves in the direction opposite to the field line. Okay? Particles interact with other distant particles by setting up fields all around them. Okay? These fields in turn affect other particles. So the field, this particle is feeling the field. It doesn't care what created the field. Okay? It could be one particle that created the field, a million particles that created a field. It doesn't know and it doesn't care. Okay? And so here's an interesting question. Okay, so here are two particles. This is charged, this is charged. Now if I jiggle this particle, how does it know that you jiggle the particle?
The field moves with the particle.
When does it know that you jiggle the particle?
From the field of
Instantly?
force.
Yeah. And with the speed
takes time
of,
to
the speed
drop.
of light.
It will know. So at the speed of light. So that's okay. So okay. So that's to answer that kind of question, you need to learn electrodynamics, which is a little complicated. Okay. So electric field lines just tell you the field at that location is tangent to that field, tangent to the field line. Okay. So here are some rules. Field lines begin at positive charges and end at negative charges. The greater the charge, this is just for illustrative purposes, so these are the rules we come up with. Greater the charge, more field lines are drawn out of the field, out of the charge. Okay? And field lines end at negative charges. So electric fields in general are functions of time and spatial coordinate. So so you see, this is an electric field at every location. Okay? It's a vector field. Okay? That means at every location you associate a vector. Okay? Now what is this? What I've drawn is, I'm sorry? The electric field at position. This is electrostatics. We are not letting you jiggle these particles. If we let you jiggle these particles, then the electric field becomes time dependent. Okay? So right now, we're not letting you jiggle the part. Okay? So all the electric fields are stationary. Okay, so here's a dipole, a positive charge and a negative charge. At this point, the electric field is tangent to that. Again, we will plot this in a lab, I guess. So at this point, the electric field is like this. At this point, the electric field is like that, okay? Electric field lines indicate direction in which a positive charge would move when placed at the point. Okay. So let's say these are field lines created by some charge distribution. Okay. When we want to indicate a stronger field, we draw more lines, so the density of lines is increased, and you want to indicate a weaker field, then the density of lines decreases. Okay? That's how we indicate weaker and stronger fields. Okay, so the field lines like that. A positive charge placed will feel a force tangent to the field line, and negative charge will feel a force tangent to the field line but in the opposite direction. Okay. The force felt by a test charge in the electric field is given by that. Okay, so here's a very interesting point. Here's what this equation is saying. What create electric fields? What produces electric field lines?
Everything?
Charged particles. Charged particles create electric field lines. How do you detect these field lines? You need other charged particles. So there's a beautiful symmetry. Whatever creates it, that's what you need to detect it. A mass creates a gravitational field. To detect that gravitational field, you need other masses. Okay. All right. So the electric field is defined as the force per unit charge. Okay. Here's a positive charge, and the field lines radiate like this. And if you measure the strength, the further out you are, the weaker the field gets. Okay, and the direction is again, electric fields are vector fields, and the strength of this field decreases as you go further out. Okay, so at a distance r, the magnitude of the electric field is given by, again, Coulomb's constant Q, the charge, divided by r squared. Okay, so you go twice as far, the electric field strength decreases to a quarter of what that value was. R hat is the radial vector, unit radial vector pointing outwards. Yeah, that's r hat at this point. Okay, so the strength of the field decreases as 1 over r squared. Field lines point toward a negative charge. And again, just like forces, you have superposition principle for the electric field. If you wanted to calculate the electric field due to a bunch of charges, calculate the electric field due to this guy at that point, due to this guy at that point, and they're all vectors, and the net electric field is just the sum of all those vectors. So if you had this many charges to find the electric field at that point, how many? You had to sum 8 vectors. To calculate the electric field here, you had to sum 8 more vectors. At every point to find the electric field, you had to sum a whole bunch of vectors. What if you had 100,000 charges? Yeah, at each point. Nobody would do physics. So you'd better come up with smarter ways to calculate electric fields. I'm sorry? So we will talk about that next chapter. Gauss's law. Okay? We'll give you smarter ways of calculating electric fields for charge distributions. Okay? An electric dipole is two equal and opposite charges separated by a distance. Okay, the dipole is here the Q, and here's D, and it's a vector pointing from the negative charge to the positive charge, okay? And this is a dipole, okay? So there is a dipole. Uh, and these guys are important because in nature you find dipole, and in fact, life probably couldn't have existed without this dipole. What is this guy?
Water.
It's a water molecule. The oxygen is greedy for electrons, and the hydrogen will give up his electrons. So for this water molecule, the center of positive charge is somewhere there, and the center of negative charge is there. I'm just exaggerating. So this water molecule has a dipole moment, okay? And it's like that. What is this guy? Methane. So, and the methane molecule, the center of positive charge and the center of negative charge are right on top of each other. So it has no dipole moment. Okay? For an oxygen molecule, it has no dipole moment. Okay? So a lot of molecules don't have any dipole moment. Water molecule has a dipole moment, and we are thankful for that. So here's why we're thankful for that. So if you take molecules like this is a molecule like this. This is these are lipids, okay, phospholipids. These molecules have a head like this, which is a polar head and a neutral tail. Okay. Now here's the deal. You take a water and you put a bunch of these guys like that. Just throw a bunch of these molecules in there, okay? And remember, so this, oops. Okay, so here is a water molecule. Oops. This end is negative and this end is positive. This guy will line up like that. You guys understanding what I'm doing? So you take a bunch of these molecules and throw it in water. This is what happens. They form a ball. Why that configuration? That is the lowest energy configuration. Here's the inside, here's the outside. Life, environment. All thanks to the dipole moment of the water. So you can do all kinds of neat stuff. All right. You saw that the electric field due to positive charge falls off as, here's just the magnitude as r squared. If you have a dipole like this, you calculate the electric field along the axial points. Along these points, it's harder to calculate. We'll just calculate along the axial points. Z is this distance. That distance is Z from the center of the dipole. And you see the electric field falls off as Z cubed. And this makes sense. The further out you are, so let's say you have a positive and negative charge here. Okay. Nolan can see these positive and negative charges separated. But now if you were in New York, what would you see? You'd see a neutral particle. Okay. So the further out you are, the field falls off as z cube and you see it as a neutral particle. Hmm?
But it's not neutral.
Right, right. Well, I mean, so to see the grainy nature on your shoes, I have to be close enough. If I go far, I don't see the grainy nature of your shoes. Yeah. All right. So here's a thundercloud, and you want to find the electric field due to the thundercloud here. What you do is you guys are all calculus experts. You break this thundercloud into tiny little pieces. Calculate the electric field due to this piece, then calculate the electric field due to that piece, and so on. And then you know the superposition principle. You just add up all those electric fields. And adding up is doing integrals. Okay, so this will be a triple integral. Of course, that's an impossible integral to do unless this has a very symmetric distribution and all that kind of stuff. All right. Now, in preparation for the next chapter where we want to calculate electric fields for uniform distributions and all, we'll define certain things. So volume, charge density. So for instance, this is a thundercloud, and what we'll do is in reality this doesn't happen so, but we'll smear it evenly with charges. And then we'll ask how much charge there is per unit volume. That is this volume charge density. Total charge divided by the volume, where it's evenly spread. Sometimes what we want to do is we want to spray the walls with charges evenly, okay? Then you want to know the surface charge density. There will be times when we spray charges evenly along a wire. Then you want to know linear charge density. Okay? Here's a ring of charges, okay, evenly spread, and if the total charge is Q, this portion has an electric field like that, and this guy will have an electric field like that. So anyway, if you go along the axis, the electric field is along the axis. So this is a very contrived situation. A ring of uniform charge, we give you an expression for the electric field along the axial points. We can't give you an expression on along any other points. Okay? So along the axial points, the electric field is the total charge on the ring. K, X is how far you are from the center of the ring, and A is the radius of the ring. There's the expression. For the electric field along the axis, along these points. There are all these points where we can't give you the electric field. Yeah. We can give you an integral, impossible integral to calculate, but that's about it. Yeah. Here's a disk of charge, uniformly distributed charge, sprayed charge, and we can give you the electric field along this axis. We can't give you the electric field at any of the other points. We can give you an integral, impossible integral to solve. Okay? So the electric field along these points is that. Z is that distance. R is the radius of the disk. All right. In the next page, what we'll do is we'll let the radius go to infinity. Okay? So this will be a sheet, an infinite sheet charged uniformly with charge. We'll find the electric field there. If R goes to infinity, what happens? Z is finite, this goes to 0. And the electric field is just 2 pi sigma Ke. Okay, the electric field from a uniformly charged sheet, the electric field there is sigma is the charge density divided by 2 epsilon naught. This is a constant. So let's make sure we understand this. That's the electric field there. What is the electric field there in New York? I'm sorry?
What does it look like, or what is it?
What is it? What's the value of it? Same thing? So here's the sheet of charge. The electric field here is the same. It's the same in New York. It's the same in the next galaxy. If this sheet is infinite, in this half of the universe, it's pointing like that. In this half of the universe, it's pointing like that. The magnitude is the same everywhere. Amazing. All right, so here are some electric fields, strengths of electric fields in various environments. Inside a fluorescent light bulb, the electric field is 10 Newton per Coulomb. Okay. Anytime you see a spark in air, lightning is a big spark, the electric field there is greater than 3 million volt per meter, or 3 million Newton per Coulomb.
So even when you just touch a doorknob and there's static?
Yep, so where that spark happened, there, the electric field strength was 3 million volt per meter. Any other place you're aware of where sparks happen? In a car, between the spark plugs. So every time you're sparking, the electric field there was 3 million volt per meter. All right, so since you're in a physics class, you want to understand what is happening. Okay. So here are air molecules. These guys are all neutral. Yeah. So let's say there's always stray electrons, homeless electrons floating around. And let's say we have a electric field like this. And what will happen to the electron? It'll start accelerating in this direction, okay, in the opposite direction. It'll pick up speed, but pretty soon it runs into a molecule and it'll lose all its speed. Now, if this electric field happens to be greater than 3 million, you will learn volt per meter. That is, every meter, there's 3 million volts. That's the strength of the electric field. If the field is greater than that, now what will happen is this electron will accelerate and it'll pick up enough speed before colliding where it starts knocking off electrons. So that was the critical field. Okay? So it'll start knocking off electrons, and pretty soon the air becomes conducting. Okay? So if you have a thundercloud here, the thundercloud can discharge through this conducting path. That's the lightning. Okay? So every time you see a spark in air, something created an electric field that was greater than 3 million volts per meter. Okay? And of course, that doesn't last too long.
Is that why if you're like higher up, you have a higher chance because if there's less column of air, it has to be less tall?
So if you're higher up, what happens? You need a smaller electric field. Very good, Eli. You can keep your dollar. All right. So in the next chapter, we'll learn about capacitors. Okay? Capacitors are just a parallel plate capacitor is two metal plates. You connect a battery when this is positive. This is positively charged, this is negatively charged. And you have an electric field in that direction. Okay. So if you put a positive charge here, and the electric field is like that, it'll move toward the negative charge. And these guys are useful. These devices are useful. Okay. So here are two plates. This is positively charged, this is negatively charged. And you can shoot beams of electrons. These are easy to produce. Okay. And then, you can make electrons hit a phosphorescent material. And when the electron hits that phosphorescent material, the phosphorescent material will light up. It'll emit light. And that's useful. That's how TVs worked in the old days. Okay. So here's a cathode electron gun, which is spitting out electrons. Here's a beam of electrons. And this set of plates deflects the electron beam vertically. Okay, if you make this positive, the electron beam will deflect that way. If you make this negative, it'll deflect down. So depending on the charges you put, and these two plates deflect the beam horizontally. And so you can make the electron beam hit anywhere on this monitor, which is coated with phosphorescent pixels, and you can draw pictures using electron beams. And in the old TVs, you had to do this. You had to draw a picture 30 times a second. Okay. All right, here's something very interesting. So here's our friend, a water molecule. Here's the so here's the center of negative charge. Here's the center of positive charge. Okay, so let's look at this guy. So let's say we place the water molecule in an electric field. Okay, now I'm just going to draw the water molecule as a dumbbell. There's the positive charge, there's the negative charge. We place this in an electric field. Okay, what does the electric field do to this positive charge? It exerts a force in this direction. What does the electric field do to the negative charge? They're equal and opposite charges. So the force is in opposite direction. So if you place it in an electric field like this, a water molecule is turned like that. And once it lines up with the electric field, it'll stay there. But let's be mean to this water molecule. Good, so there was the electric field. The water molecule is turning. Now as it's coming there, we'll switch the electric field. Now it's going like that. We'll switch the electric field again. So if you can switch the electric field back and forth, you can jiggle the water molecule. And that's what a microwave does. 5 billion times a second. So that's how you heat the water in your food. You're heating the water in your food, and then the water distributes that heat. All right, so that's how you heat your food. Okay, so if you have a dipole, you place it in a uniform electric field, you exert a torque on the dipole, and the torque is P cross E. Torques, what do? They turn an object. They give an object spin. Okay. All right. What does this guy have? Potential energy, and it gets converted to kinetic energy. So you put this dipole in an electric field, it must have potential energy because that can get converted to kinetic energy. Okay, the potential energy of the dipole is given by P dot E, negative P dot E. Okay. So again, if you have dipoles, you can do all kinds of fun stuff. Put those dipoles in electric fields and so on, and you can do them. Okay. So if you, like I said, if you switch the electric field back and forth, you can jiggle the molecule and heat things up. Okay. All right, guys. That's the end of the chapter.